Hi, viewers. This is Emmanuel Azanlerigo Explains Chem. Today, we are moving on to the next level called the wave mechanical model of the atom. Rutherford's model has certain limitations, remember. Niels Bohr also has certain limitations. And we observed that one of the limitations of Niels Bohr model was that it could not explain the light spectrum of multi-electron species, as well as explain why light spectrum split in the presence of electric and magnetic field. Hence, we need a new model of an atom to describe that. The new model is called the wave mechanical model of the atom, and this talks about the electron behaving as a wave at the same time as a particle. This model was developed by a scientist called Edwin Schrödinger in the year 1926. Based on his model or his idea, Heisenberg came out with a principle and says that the electron will behave as a wave or behave as a wave. Then it is not possible to measure the exact position at the same time the momentum of an electron with accuracy. That is what Heisenberg said. Why did he say that? Because waves normally spread out. And because waves keep on spreading out, it is not possible to measure the exact position and location of an electron. You will ask me, how is it not possible? Now, let's imagine this way. Especially, let's say you want to find out the position of an electron. You must use a particle that is smaller than an electron with a high velocity. And this particle will have a shorter wavelength. When you fire this particle towards that electron, it hits the electron and produces a flash of light. By so doing, you'll be able to determine the position of an electron, that, electron was here. However, by hitting the electron, it will increase the speed of the electron, which means that you will not be able to tell the exact speed or momentum of the electron at that particular time. You may also say that why don't we use a bigger particle with a lower speed? If you use a bigger particle, or what we call a particle with longer wavelength, it may not be able to affect the speed of an electron, but it can tell you the exact location of an electron. And that is what Heisenberg said, that it is not possible to determine the exact position and the exact momentum, also called velocity, of an electron with accuracy. And therefore, to be able to describe an electron's location, an electron's orientation, and electron's energy, we need a set of numbers that we call quantum numbers. These numbers are mathematical calculations that were developed by Edwin Schrödinger. But this video is beyond the scope of this video. We are just moving on to what quantum numbers gave us. These are the pictures of Edwin Schrödinger, and this is a picture of Heisenberg. I salute them. Let's move on now. Quantum numbers. As we all know, to search for a particular person in this world, 4 things are needed. You will need the country of the person. You will need the city in the country at which the person resides. You will also need the street number and the house number. Similarly, identification numbers are required to locate a particular electron in an atom. These identification numbers are called quantum numbers. By the end of this video, you'll be able to explain what quantum numbers are. You should be able to identify the 4 kinds of quantum numbers. You should be able to explain what each quantum number describes and assign quantum numbers to electrons in different orbitals. Now, let's flow on to the objectives. Achieving of the objective. Quantum numbers. Quantum numbers are integers or half integers that are used to describe the properties of an electron in an atom. That is that. Quantum numbers are just integers or half integers that are used to describe the properties of an electron in an atom. We'll get to understand why we said half integers. There are 4 types of quantum numbers. One of them is called the principal quantum number. And the symbol of the principal quantum number is n. This quantum number was actually identified by Niels Bohr. When he said electron occupies specific energy levels, he was able to identify principal quantum number. What does it do? The principal quantum number determines the energy level and the size of an electron cloud. Remember, according to Niels Bohr, the lower the shell, the lower the energy. The higher the shell, the higher the energy. And we know principal quantum number talks about the shells. So it helps us to describe the energy level of an electron as well as the average distance the electron is away from the nucleus. Its values are, the quantum numbers are values of 1, 2, 3, 4, symbolizing the first shell, second shell, third shell, fourth shell, and so forth. And the notation, in terms of letters, we have the KLMN. Remember this in JHS, KLMN. That's the notation. The next type of quantum number is called the angular momentum quantum number, also called the azimuthal quantum number. And the symbol of this quantum number is small l. What does it do? Indicates this angular momentum indicates the shape of the orbital or the subshell. Inside the shell, we have subshells. So the angular momentum tells us the shape of these subshells or orbitals. In terms of values, the values of L is 0 to n minus 1, where n means the principal quantum number. Notation: when L is equals to 0, we call it the s orbital and the shape is spherical. When L is equals to 1, it is called the p orbital and the shape is dumbbell. When L is equals to 2, we call the d orbital and it's complex. When L is equals to 3, that is the f orbital and it's very complex. Let's get some examples here. For example, if n is equals to 3, L can have values of 0, 1, 2. That is from 0 up to n minus 1. Remember, L can never be equals to n. It's always less than n. So when n is 3, L can have values of 0, 1, 2. 0 stands for S, 1 stands for P, 2 stands for D, which means 3S. The 3 stands for the main shell, 3S, 3P, 3D. So these are examples under what we just did. Another example is that if n is equals to 2, then L can have values of 0, 1. Remember, it's always 0 up to n minus 1. So 0, 1. And the 0 stands for S, 1 stands for P, which means in designation we have 2S and we have 2P, as we see that respectively. So inside, it only means that in the second shell we have 2 subshells. We have S and we have P orbitals in the second shell. I must note that when you count them, it's equals to the numerical value of n. For example, 1, 2 is equals to the 2, and it's equals to 2. And here too, 1, 2, 3 is equals to 3. So that is why when you count them, the numerical value equals n. Let's move on to the third type of quantum number called the magnetic quantum number with symbol m. Some books say ml, but we are using m here. What does it do? The magnetic quantum number specifies the orientation of the orbital in space. Orientation talks about the direction in which the orbital is facing in space. The values of m. Remember, m depends on L. Values of m is always equals to minus L to positive L, including 0. Which means that when you know L, you can know the possible values of m is always from negative L to positive L, including 0. And that will give us 2L plus 1 orbitals, the number of orientation that you can have. The possible orientation that you can have is 2L plus 1 orbitals. Example: if L is equals to 1, then m is equals to minus 1, 0, positive 1. This gives us 3 different orientations. Remember, L is equals to 1 means P. So M tells us that the p orbital can have 3 different orientations, and that is why we have 3 possible values of M. You may want, so that's also 3 p orbitals. Some books will say that it helps us to determine the degeneracy of the orbitals. How many degenerate orbitals will it have? It's the same as the possible orientation that it will have. Another example. If L is equals to 3, then N can be -3, -2, -1, 0, +1, +2, +3. When you count them, it gives us 7 possible orientation, which means that 1, 2, 3, 4, 5, 6, 7, and L equals 3 means F orbital, which means that the F orbital can have 7 possible orientation. Some will say that 7 degenerate orbitals. If you can use the formula 2L plus 1, so 2 times, if L is equals to 1, so 2 times 1 is 2 plus 1 is 3, that's why we have 3. If L is equals to 3, then 2 times 3 is 6 plus 1, 7. You can use the formula to give you the summary of the number of possible orientation. Note, it is this magnetic quantum number that was able to explain the splitting of the spectral light. Remember, we made mention that when an electron is moving, when a charged particle is moving, it has this kind of magnetic field. Which means that when you bring it in the presence, or you bring magnetic field closer to it, you expect interaction. And the possible ways that the orbital can occupy will tell you the possible splitting of the orbital. Which means that p orbital will split into 3 in the presence of the magnetic field or electric field. So magnetic quantum number explains the splitting of the spectral lines. Remember, Niels Bohr only stopped at principal quantum number, and that's why he could not explain the splitting of the spectral line. The wave mechanical theory made us understand how or why the splitting is done. Take note of that. The fourth one. Before I add the fourth one, remember that when the splitting of the spectral lines in the presence of a magnetic field is called the Zeeman effect, while the splitting in the presence of electric field is called the Stark effect. You may not need that for this level. The fourth one is what we call the spin quantum number. The spin quantum number has, the symbol is S, small s. Some books will write ms, but we are using S. The spin quantum number describes the electron's spin direction. It makes us to understand that there are possible ways the electron can spin. It can either spin clockwise or it can spin anti-clockwise. So the spin quantum number describes the spin of an electron. The values of the spin quantum number, the values can either be positive half, which represent up spin, and we have negative half representing down spin. Remember, these are mathematical values. And this was why I said that quantum numbers are either integers or half integers, because the spin quantum number is an half integer. Alright, in summary, we said that we have 4 main quantum numbers. We have what we call the principal quantum number, angular momentum, magnetic, and spin. The symbol of the principal quantum number is small n. The symbol of the angular momentum is L, magnetic M, spin is S. What it describes. Principal quantum number describes the energy level and size of the shell. Angular momentum describes orbital shape, that's the angular momentum. Then magnetic describes the orientation of the orbital, while spin describes the electron spin. That is the important what they describe, or their definitions. Possible values. N can have 1, 2, 3, 4, 5 going, while the possible values of the angular momentum is always 0 to n minus 1. And the possible values for magnetic quantum number is always minus L to positive L. The possible values for spin quantum number is positive half or negative half. Example. N equals to 3 means third shell. L is equals to 1 means p orbital. M, if L is equals to 1, M will be positive 1, 0, 1. And S is either positive half, that's up spin, or negative half, down spin. Let's do some quick exercise here. If N is equals to 2, what are the possible values of L? 0, 1 is your answer. If N is equals to 1, what are the possible values of M? Negative L, negative 1, 0, positive 1. How many electrons can fit in one orbital? 2. Each orbital can take 2 with opposite spins. Remember the spin quantum number. For an electron in 3p orbital, identify all the quantum numbers. Solution. 3 means the principal. So for 3p, n is equal to 3. But L is equal, this is specific, the P is the L. So P stands for 1. So n is equal to 3, then L will be equal to 1. If L is equal to 1, ML will be positive 1, negative 1, 0 to positive 1. Spin is positive half or negative half. So note, when they specify the orbital, like 4s, n will be 4, L will be 0, because S stands for 0, and n will also be 0. Take note of that. What is the principal quantum number for 2s? The principal quantum number is 2. The number always tells you the principal quantum number, so it's just 2. What values of L for a d orbital? What is the value of L for a d orbital? D orbital, the value is 2. Remember, 0 for s, 1 for p, 2 for d. What are the 2 possible values of spin quantum number? Positive half, negative half. For n equals to 4, list all possible values of L. 0, 1, 2, 3. How many orbitals are in the d subshell? D, the value of d is 2. So 2L plus 1, that's 2 times 2, 4 plus 1, 5. So that's a possible, this one. Evaluate the possible values of magnetic quantum number m for an electron in an orbital with L equals 2. If L is equal to 2, then m will now be negative 2 to positive 2, so 5 values. Since m ranges from negative 1 to positive 1, remember that. Explain why an electron in 2s orbital cannot have L equals 2. An electron in 2s orbital cannot have L is equals to 2 because if n is equals to, it is 2s, specific, means n is 2, L is 0. So there's no way L can be 2. L being 2 means D, but we are not talking about D. So note, n equals 2, L can only be 0 or 1, since it ranges from that. Take note of that. Alright. Importance of quantum numbers. The importance of quantum numbers are, it describes the energy of an electron, it describes the possible subshells or possible orientations of an electron. It also helps to describe the energy of an electron. It helps to describe the shape of an electron, and it also helps to describe the spin of an electron. These are the importance of quantum numbers, just as we did. Orbitals. The last section for this video is on orbitals. When we talk of orbitals, orbital is the volume of space, any space around the nucleus where there's a high probability of finding an electron. It's called an orbital. Remember, we said that the orbitals are the s, p, d, f. The s orbital is spherical. This I got it from mathematical calculations. It's spherical. The p orbital is dumbbell, and this is the shape of a dumbbell. This side is the nucleus, and that is what we call the node. The node is the region where there is no probability of finding an electron, while the broad portions here are what we call the loop. The loop are where there is high probability of finding an electron. Take note of that. So this is s orbital, which is spherical in shape. It has no direction. It's just spherical. The p orbitals are dumbbell, which can either be on the x-axis, the y-axis, or the z-axis. So these are the orbitals. And the d orbitals, we have 5 d orbitals. We have what we call the d orbital in the z-axis, called the d z square. And these are the 2 dumbbells that we talk about, complex. 2 dumbbells, 2 dumbbells. So d orbital actually have 2 dumbbells, except one of them that is donut in shape. So take note of these. Remember, the question will ask you to draw the shape using the diagram to describe s and p orbital. Let us know that it is spherical with the Cartesian plane. Let us know it is dumbbell, and let us know the possible orientation in the x, y, and z axis. Thank you so much for watching this video, and next time with me, we shall look at the applications of these quantum numbers.